Log on, tune in, find out. Another good idea from Cambridge.
Introduce Nicola Tilt from Procter and Gamble, who's coming to tell us all how to do our washing.
Thank you. I work in the Newcastle Innovation Centre, where we do specialise in fabric and home care. So a lot of our work is around washing powder. So, and that's a particular example that I'm going to talk through today. I agonised over what to talk to you about today, and chose a mixture design that I've come across recently. And this is, we do a lot of mixture designs, as you can imagine, sort of building up, formulating washing powders. But because of the complexity of the way that washing powder is made, which people probably don't even understand the hideous complexity, I was astonished that there's so much involved in making washing powder. Then I chose the mixture design because I think it's a sort of an interesting class of designs. And this particular problem that I'm going to talk to you about is something that I couldn't solve myself. So a colleague of mine in the US gave me some help with this, and he's actually recently published a paper on mixture designs, and I've followed some of the theories that he's used in that paper. So I'm sort of talking. So any difficult questions, I'll just blame him and get you to read the paper. But what I'm going to talk through to start with is just basically how we make washing powder. Don't worry, I'm not going to go through all of the complexities because I'm a statistician and not a chemist, but just to give you a sort of basic idea of what the process is and what the complexities are that are involved in it. And I'm then going to talk through this specific case study problem that I had quite recently. I'll give you a little bit of statistical background. I'm not going into details on that, but just for people who aren't familiar with mixture designs, and then the issues that I faced relative to this specific problem and the design solution that I came up with. You'll note the question mark there because this is a particular solution that I came up with, but whether it's the best solution or not, then I'm sure some people can add some points on that. I am just talking about the design rather than the analysis as well. Some of that is due to time, some of that's due to my talk having to go through strict legal procedures before I could come and talk to you about it. So I am focusing on actually the design that I used for this particular problem. So this is how you make washing powder, you see, and you all thought that you just got a load of chemicals and put them in a test tube and got washing powder, but the process is actually very complex, and this is specifically for washing powder because of course you're mixing sometimes a lot of liquids and stuff, and yet you want to come out with these beautiful fluffy granules at the end of it, and that's where the complexity comes in. As I said, I'm not talking you through the whole process. There's whole books on how to make washing powder, I was amazed to discover. So none of this is proprietary. Apparently everybody knows this. But so the key elements that I want to focus on here are this first part here, where we're actually making what I'm going to refer to as the base powder. So if you think about it, it's sadly not as simple as this, but if you think about it, that we're basically making some kind of sort of base vanilla type powder, and then we're adding all the extra stuff. So when you have your nice smelling Ariel, you've got extra things in it, extra perfumes and nice blue speckles in your powder and things like that. So if you think about that as this being the base powder, and then this base powder, which is actually liquid, it's some kind of gooey, slurry mix, a bit like porridge, that then goes through all of these tanks and pumps and drying, and it involves an enormous tower. So we have one of these in Newcastle. It cost rather a lot of money, and the council have never been very pleased about it, but you need an enormous tower that you can then drop your powder from to dry it in a way that you end up with these nice fluffy particles. So we've got a mixture of chemicals here, but then before you get your lovely box of Ariel at the end, you're adding another load of chemicals there as well. So there's two stages in which we add mixtures of chemicals. And that's why we tend to have more complex mixture problems, because of having different stages at which we add mixtures. Now luckily a lot of the time we're just dealing with one part of that, but this is why the problem can become more complex. The actual problem that I was dealing with was for the process team, and they were trying to look at the base powder composition essentially at one of our plants. And what they wanted to do really was just to optimize some of their process conditions. So they wanted to look at what particular mixture of the base powder was going to optimize some of to make it more processable, if that's a word. So essentially the types of things they look at are the density of the finished product. You want to make sure that it fills the box. They look at the size of the granules. You don't want huge clumps, neither do you want very fine powder. You want to have nice evenly sized granules. And they also measure something called the cake strength. And again, think about your washing powder and you might get nasty big lumps in the bottom. And the cake strength is really just a measure of how easy it is to break those clumps up. So essentially those are some of the measures. They have a whole range of measures that determine how processable this is, but those are some of the ones that we were looking at. The constraints that they came to me with were in this kind of format. Again, this has been all useful information has been removed from this slide. So I'm talking about BP being this base powder, and then I've got a series of raw materials labeled raw material 1 to 5. So I've basically, my base powder can be between 30 and 60% of my finished product. This first raw material then makes up a certain number of parts of my base powder, and I then have these ratios of my raw material 1 to 3 of the other raw materials there. And the last but not least constraint is that the sum of these 4 raw materials has to be less than or equal to the total number of the blown powder parts. So I have got this 5th factor that I can as such balance with. So given this set of constraints, I set about trying to formulate a normal kind of mixture experiment. Tried then to formulate a more standard type of mixture experiment and ended up going round in circles and scratching my head a lot. When I then picked up the phone to a colleague in the US who gave me some assistance, so I will be acknowledging him a lot. So for those that are not that familiar with mixture designs, I mean the key thing about a mixture design is that we have this inherent dependence that all of our components have to add up to the whole. So rather than having independent factors, we've got several components that add up to our whole. So we're already in this sort of mixture setting. But I have to have 2 different mixtures, because as well as having my base powder, I've also got this constraint here on the level of my base powder within my finished product. So I've therefore got this mixture of mixtures, this base product plus a set of admix components makes up my finished product. I'll show you a clearer diagram on that in a moment. So your mixture of mixture design, as the name suggests, is a mixture of several mixtures. So you might have 3 different components that in themselves are mixtures that you then mix together to make up the whole thing. The sorts of terminology that's used, and I'll just flash this up just so that you know what I'm talking about. But we tend to talk about it in terms of the major component. So you mix a series of major components to make up your whole. The things then within your major component are your minor components. So you're basically mixing a number of major components to make up the whole thing, and the minor components are within that. And you can generally then have linear constraints based on those, and that's your usual setup of your mixture of mixture design. I find this diagram easier to get my head round in that this is your final product, and you've got these major components that make up that final product. Each of those major components is made up of a mixture of the minor components. It's getting your mouth around it as well as your head around it is sometimes challenging. So the specific example that I'm dealing with looks like this. So I have actually only got two major components, the base powder and what I'm calling this admix. And my admix, I'm assuming here, has fixed composition, so I'm not having to deal with that. But I have to deal with it in the sense that I'm mixing it to make up my finished product. So that's the only way that I'm dealing with that. And I've then got these 5 raw materials that I'm mixing to make my base powder. And I've got those various constraints that I talked about on those initial raw materials. So having looked through the literature, there's plenty of documentation on this. There's papers in journals, etc. And also in sort of, I revert to jump help menus as well in terms of how we look at mixture of mixtures. And this was the sorts of models that I've seen quoted, in that we're looking at this so has been referred to as a multiple Chaffee model. I think it's got other terms as well, but there's various different, I think the original model was the multiple Chaffee, and then there was various things on top of that to generalize it some more. But basically where you're looking at this product of your functions of your minor components that are usually polynomials, and then crossing that with a function of your major components. The paper that I was referred to, which is recently published in Technometrics, and a colleague of mine was involved in that with a university collaboration. They looked at the sort of disadvantages of using this type of model, and there's a whole host of things that they go through in that paper, which I'm not going to go through, but I'll give you the reference for that if anyone's interested in that. But the key thing to me was, in practice, what am I going to do? I work as a statistician, as I had discussions with a lot of you in the break, is that I am the single statistician on my site, and therefore my key goal has to be, how am I actually going to do this? So that was really the key thing here, is what was the practical implementation for me of actually creating a design for these people here. And the key issues that I had here is that the constraints that I'm dealing with are not linear. I've got these ratios within my constraints, so that was causing me a problem. And also the types of designs that I was seeing could be quite large, and the design that I was being asked for, they were basically just looking at some of the processability. So this wasn't going to be a large experiment where they were going to be looking at all of the performance and all of those kinds of things. They just wanted some quick answers on the processability for this particular plant. So there was going to be definitely constraints in the number of runs that they could look at. So those were the key issues that I needed to get around. So based on this paper, the sort of process that I looked at was generating a candidate set of designs. So using a computer algorithm to make this candidate set of designs based on the constraints of my minor components. Then looking at an optimal subset of that, because that candidate set was going to be big. So then picking an optimal subset of that, and then crossing that with the major components to give me the final design. So that was the step by step. I complain all the time that people want recipes for doing things when I'm working with the chemists and the engineers, and I found myself in exactly the same situation here, going, okay, what exactly do I need to do? So this was really the process that I needed to go to. The model then that the paper proposed was, they're calling it a major-minor model, but it actually turns out to be a subset of the model that I showed before. And the difference is that you're eliminating terms that are products of the major component proportions with unrelated minor components, which terms that really physically don't really make sense anyway. So, and because you're taking away that subset of points, you end up with less parameters in your model and therefore need less runs in your design. And the algebra of that is shown in the paper, so I don't feel like I need to show it here. So to create my candidate set, now we use JUMP a lot in our work, so all the work that I've done has actually been in JUMP, but it can equally be done. I believe the paper used R, and it can be equally done in other software, but it was very easy to implement using JUMP software. So I created this candidate set, and I actually used, I broke up my factors into even 6 areas and basically created a grid design. So I'm basically looking at a grid. I used the factors being the percentage of this raw material 1 and then the different ratios to raw material 1 of 2, 3 and 4. So that was, you know, that's exactly how my constraints were set out, and so I translated those constraints into the different levels that I needed in this candidate set. So I create then a set, a grid basically of runs, which was 1,296 runs. Now if I then went to my colleagues and told them that's how many runs they needed, I wouldn't be very popular. And being the only statistician on site, you need to make yourself more popular than that. So going back to the constraints, the only ones that I've dealt with are these 4 in the middle here. So I still need to think about this constraint here, that the sum of those parts needs to be less than the whole of the BP. So that was the next one to deal with. And basically, you know, you can back calculate and work out the proportion for each of those. I know the proportion of my raw material 1, so I can calculate the proportion in my base powder of raw material 2. So I then could calculate that for each of the runs and simply eliminate the ones that didn't satisfy that constraint, which in this case was actually only 54. So I'm still left with 1,242, which still would be a little too many to tell anyone they needed to run. So I then just picked an optimal subset, and again, this is where I needed software to help me to pick that optimal subset, and so I did that using algorithms in JUMP. So using the custom design platform, I could actually pick out an optimal subset of that, and anyone who's interested, JUMP users, I can talk that later. I wanted to fit a quadratic model, so I would end up needing to have 16 parameters. So I picked an optimal subset of 20 runs. So out of the 1,242, I could pick out this much smaller optimal subset. So I've now dealt with 5 out of my 6 constraints, or is it 4 out of 6? Anyway, I've still got that constraint left that relates to the proportion of my base product relating to my finished product, and that's where I need to then cross the design. So basically, the design gets crossed based on different levels of that base powder. The base powder could be between 30 and 60% of the finished product. Because I wanted to look at that in a quadratic manner, I just chose 30, 45 and 60 and took 20, an optimal subset of 20. I took a different optimal subset each time, so that I ended up then with 60 runs at the end of my experiment that I could then go to the process people and give them this optimal subset of this design of 60 runs at the end of it. I think that's almost it, actually. Just check. Yeah. No, it was. So 60 runs then was a manageable experiment for the type of experimentation that they were doing. And this gave me sort of a really practical way that I could go through and do this type of design and satisfy all the constraints that I needed. So that was the process that I went through. The paper that I have referred to is this technometrics paper from earlier this year. I have a copy as well with me, and my colleague William Brenneman, who's at Procter & Gamble in Cincinnati, worked on that with these guys from Ohio. So this was what sort of led me down this route, and I'm really interested to know what sort of other options people think about for that type of design. I was in a huge hurry, therefore didn't have time to do huge amounts of research on this in terms of being able to give people a design that they could implement. But this seemed to give me a really practical option, and although I'm not sharing results, this was a successful design, and we did get some really nice information out of it. So once the design was set up, and I'm not, to be honest, talking through the results, once the design is set up, doing the analysis was very straightforward. So the interest for me was in actually setting up the design here. The results just followed nicely once the design had been created in this way. So it'd be interesting to know what people think and what other options are available for doing this kind of design.
Questions?
I'm just curious why you didn't choose a standard composite design with the extra 5 runs. Would that have been a big deal? You picked a 20-run design. I think the standard
Yes,
composite
it
design,
would have been a big deal.
in which case, why didn't you run a small composite design for 50 runs?
Yeah, I mean it was essentially, but I wanted to do a different optimal subset for the different pieces. So it was more the composite. Would the composite design have then allowed me to have looked at
Could I say I don't understand the question?
Yes, you can.
Thank you very much. You're doing a mixture experiment.
Yes.
What is a composite design in
Yes.
that context?
I think you mentioned that you were considering.
But I had all of those constraints on it, so I had the mixture.
No idea what a composite design is.
Perhaps I misunderstood what you said then. I thought you'd mentioned composite designs.
No, I didn't.
Good?
No.
Okay, that's fine. It's a pleasure to be of service. Yes.
Could I ask?
Yes,
question?
please.
Yeah.
So if I got you right, you had a different subset of 20
Yeah.
with each of 3 levels of something
Yeah.
else. So you had 60 things altogether. Were they randomised, or did you have to do all of one level of that thing and then all the second level of that thing?
They were randomised.
They really were randomised
They
altogether.
really were.
Oh, good. So then
No, they actually really were. They fight against that kind of thing,
I know.
but they really were.
Did you have to? I mean, it's like, if we go back to composite design and blocking and things, it's as though you've repeated the composite design 3 times at 3 different blocks or something. I mean, you've had 3 different large mixture experiments, but you've done something similar inside each time, is that right?
Yes,
Just scaled
yeah,
down.
Yeah.
And there's no particular reason for doing that, is there?
I'm not sure. Well, get my head around it. So,
I mean,
well, because of the way that the constraints are set up, then I don't think that I can't run it as an independent. If you,
you just have this huge list of candidate points.
I have a huge list of candidate points.
3 times as many as you
Yes.
thought you had.
Yes.
And then you could use your jump algorithm to select the best 27 or whatever, couldn't you?
Oh, yes, I see what you mean. Yes.
Yeah, isn't that? You could have done
Yes. But the yes.
Yes,
Yeah.
okay, no,
I
I mean,
think you
I'm
can.
not
Yes,
saying
I think you
should or
can.
shouldn't, but
Yeah.
you could have. Yeah, thank you.
I think so. Go on, someone else answer it for me quickly.
Yeah, I agree with Anthony. What you have to watch out for, though, is that you end up with an identifiable model that you're dealing with here, because you've got not just a single mixture constraint, you've got all
You've got
these
the second one.
sub-constraints in operation, the minor
Yeah.
components,
Yeah.
summing to one of those. So you couldn't just kind of bang it through any optimal algorithm. You'd have to be able to set up a model, as indeed Chaffee did in his simpler cases, and later people have done, Draper and Cochran and so on, so that they eliminate redundant terms, if you like, those that can be expressed as linear combinations of the components. Take those out of the model so that the model is identifiable somewhere, and then you have to search your list.
You're saying that would be a tricky thing to do, perhaps, in cases like this.
Well, I suppose it has to be thought about and implemented properly. You're not going to be able to turn to jump and say, just do this for me.
Yeah, because you've got that dependence there between the.
It's the formulation of the model where you have to watch your step there. And I'm no expert in jump. I suppose once you've worked the algebra, once you've worked the algebra out, then you probably could specify the appropriate model in jump. That's the snag. But I don't suppose jump is set up to do these mixture type structures.
Well, no, I mean you sort of have to trick it to pick the optimal subset in a sense. Anyway, it's sort of it's not an obvious option.
But they might be persuaded actually if you told them this is something that you want a lot. They're very good at putting stuff in. Sorry, I'm not giving a commercial for anyone.
How on earth do you even know that?
I don't know anything else, but you know that. Well, if there are no more questions, this can be discussed more in the break. And thank you again very much for that.